Okay, let's start. So we were discussing two-port network, incremental two-port network, and where we stopped in the previous lecture was here. So I'm writing this as y11, y22 with implied assumption that these are conductances. Just because I wrote y1 and y22 doesn't mean that they are resistances, right? Similarly, since I'm writing in terms of conductances, I converted the resistances and RS and RL into GS and GL also. So yeah, so when in doubt, you can write in terms of 1 over whatever suits you. But if you write in generally, the notion is if you use the notations like Y or G, it means conductances or transconductances. We'll follow the same notations. Okay, so this was V1, this is V2. So I'll ask you to find out what is V2 over V1. Did you do that? V2 over Vi rather. Anyone? Okay, how do you go about doing this? Solving this? Yeah, right. So you can basically write out the equations in the two loops, right? And you will get something. The way I prefer to do it is reduce the number of nodes, because the more number of nodes, the more number of equations. So input wise, you can basically Theveninize or Nortonize. So the input can become Vi GS, and this becomes GS. So that GS and Y11 become parallel. And at the input side, you essentially have one node, and output side, you have one node. You can basically have a system of two equations and write it out. So we can do it quickly here in this case. At the input side, then it will be Vi GS equal to right, and the output side it will be right. So again, this is I'm deliberately writing this in this form because you know that I'm going into matrix. So this becomes and now you can use Kramer's rule to find out what is V2. I hope you remember Kramer's rules. Long time back. So what is it? You take the determinant of the matrix here in the denominator. Numerator, since I want V2, I replace the second column with this, right? So now if we expand this, The numerator simply becomes minus VI GS Y21, and the denominator V2. V2 is in our case V0. So essentially your gain becomes, with the voltage gain becomes GS Y21 okay. So let me also mark this out as V0. Okay. So this is algebra. I mean, there's nothing fancy about this, and we can further expand the denominator to, but let's keep it in this format. So now, when you get something like this, the next question to ask: so what, right? So what insight do I gain out of this? So now the goal is to maximize, right? Maximize the gain. One might say the goal is to maximize power gain, but let's stick with voltage gain, then we'll see how power gain arrives, right? So so if I have to maximize the voltage gain, what do you think? What is the easiest way to do? Minimize the denominator, and assuming again further that all these incremental y parameters are positive. By the way, they did not necessarily be positive because they are derivatives of certain curve. So they can also be negative. But let's assume they are positive for the timing. If they are positive, then it's possible to null out the denominator by choosing appropriate values, right? If we can choose the appropriate values and null the denominator out. But there is an issue with that. And the issue is the following. I'm sure you have taken some control system courses in your UG curriculum, and I'll show you something which should resonate. So let's say I have this classical feedback structure. Yeah, this is V0. Have you seen this before? Okay. So an important distinction that I would like to make with a generalized feedback structure and this is a unilateral feedback structure, that is signal only flows in one direction, right? So both in the block G and in H, block G it flows from left to right, and block H it flows from right to left. It doesn't go both ways in either of these blocks. And also there is only one loop. So these are the two important distinctions to make while doing this analysis. The reason I'm making this distinction is, if I go back and check our incremental two-port network, so this was GS. So do you think in the network on the right, there is a feedback? Or is it an unilateral? I mean, is the signal only flowing from the source to the load, or there is some part of the signal that is flowing back from the load to the source, towards the source? There is, right? And what is which element is responsible for that? Yeah, so there are two dependent current sources. Y21 V1 is responsible for taking the signal from the input port to the output port. Y12 V1 is responsible for taking the signal from the output port for the input port, right? So there is a feedback, right? And since this is a current source, Right? These are dependent current sources. These are also unilateral feedback. When I mean unilateral, what I essentially mean is that Y21 V1 takes the signal only from input to output. It is not responsible for taking the signal from the output to input. Right? Okay, so the statement might seem confusing as to why am I saying that. Let's say you had a resistor here connecting the input and the output. A resistor is a bilateral device, right? A signal can flow this side, a signal can flow that side. So it connects the input and the output in both ways, right? So both the signal can go from input to output as well as from output to input. However, a current source or a control source, this Y1 to V2, the signal only flows in one direction, right? So you either go from left to right or right to left via each of these control sources. So hence, I can assume these blocks are also unilateral in a way. Okay. So in essence, I can model the network on the right with something equivalent to the network on the left. That's all I am targeting you. Okay. So if that is the case, so I would like to see what happens. First, let me extract the values of G and H, or first let's extract the values of G from the network on the right. So if the network on the right is similar to the network on the left, then I should be able to find out what is the equivalent G, right, in the GH plot. By the way, this G is not impedance and not admittance. This G is the gain, right? So what is V naught over Vi in the network on the left? This is G upon 1 plus GH, right? And we know V naught over Vi on the network on the right. So this is this stuff. So in the network on the left, if I have to find out G, right? What is it that I need to do? I need to null the feedback, right? Experimentally, if I have to find out G, I need to null the feedback. If I somehow set H to 0, H is the feed, some part of the output that is coming to the input. By the way, when I say, this is also another important distinction to make. When I write something like this block, in your control system textbooks, you will also have seen. So when I write something like this, what does it mean? It means if I apply an input, let's say Vx, output will be G times Vx, right? So input is a voltage, output is a voltage. And this is true regardless of whatever you connect here. Correct? Are you comfortable with this explanation? Okay. So what type of block do you think this is? In terms of the control sources that you know that exist, like voltage control voltage source, current control current source, voltage control current source, current control voltage source, right? So there are 4 types of it. It's a voltage control voltage source, right? So this is a VCVS block. Okay. And the stuff on the right, these are voltage control current sources. The feedback, similarly here, the feed in the stuff. So if I say this is H in the left-hand side is also a voltage control voltage source, right? But the H is responsible for giving me feedback from the output to the input in the network on the left, or in the block diagram in the left, and the network on the right, the feedback is coming through a voltage control current source. Correct? So that's again an important distinction. Why am I saying that? I'm saying that because ultimately, let's assume that I need to extract the value of G. For that, I have to null H. Right? When I say null H, I essentially mean that I am setting the gain of that feedback, gain of H to 0. Right? If H goes to 0, then if I observe V naught, then V naught over Vi will be G. Correct? Okay, so if I'm confusing you. So let's say I do the experiment and set So V naught over Vi when H is equal to 0, what should I get? I should get G. Correct. So that's all I'm doing. So I'm saying that in the block diagram on the left, let's say I have a block diagram on the left. Experimentally, I have to figure out what is G, because V naught in the information of V naught over Vi, G and H are embedded, right? I want to isolate them. So what should I do? I should set H to 0. Setting H to 0 is equivalent to saying that I am nulling the voltage control voltage source. Now let's turn our attention to the net circuit on the right. Here also I have a feedback, but the feedback is coming through a current source, right? I want to null the feedback in order to figure out what is this equivalent G, in order to find out the equivalence between the two networks. So what should I null? I should null current source. Nulling a current source is equivalent to saying I will open it. Okay. So in order to find G in the circuit on the right, so what should I do? I should find out V0 over Vi by setting Y12 to be equal to 0. Right. So this will be equivalent to the G on the circuit on the left. So what would I get if I do that? I just plug in Y12 equal to 0 in this, then I should get minus GS Y21. Right. So this seems to be the open loop gain of my of the network on the right. Right. When I say open loop gain, because I am again relating it to the gain on the block diagram on the left. This G is the open loop gain when the loop is not in place. When the H is 0, loop is not in place. V naught over Vi is the open loop gain. In the network on the right, there is a feedback. I am nulling the feedback. So whatever gain I will get will be the open loop gain. Right. So this will be the open loop gain. Okay. So why am I doing all these things? I'm doing all these things because of this reason. Now let's assume okay, so let's extract all the parameters, then we will do the analysis. So if this is G, what is GH? What is this GH term? So for that, I'll have to write it out and do that algebra. Otherwise, it will not make sense. So I will divide by this, right? So that I get this factor on the top and I can write it in terms of G by 1 plus something. So this becomes. Okay, and this should be equivalent to G by 1 plus GH. I'm trying to find that equivalence. Oh, sorry, correct, please. Yeah, thank you. So I know this becomes the G, and this is 1. So essentially your GH becomes minus Y12, 1. Right? Till now only algebra, no intuition, right? Only algebra. So now I want to focus on some part of intuition. So I will, since now I have broken this model down into G and H, right? So I can now fully focus on what this block diagram is telling us. So now consider that, now tell me what's going to happen if, so input is some sinusoidal input, right? And G and H can be frequency dependent and frequency independent, regardless of that. But let's assume that what's going to happen if GH is equal to -1, right? This is equivalent to saying I'm nulling the denominator, right? So I'm getting infinite gain. This is similar to the condition we were seeing a few minutes back, right? So, but the more deeper question is, what is the implication of this? Is this something that we want? This is bad, good? Any comments? Stability will be an issue, right? So even though I haven't touched stability at all till now, we'll do it later. But in order to see intuitively why stability will be an issue, consider this scenario. Well, let's assume I don't have this connection. Okay, I don't have this connection, and I apply a sinusoid here. Okay, so this is a free running sinusoid at some frequency omega naught. And the system is set up in such a way that GH is equal to -1. Okay. So if system is set up in that way, so what will the voltage at this node be? Note that feedback is null. I'm not null, but the feedback is broken. But GH is equal to -1. This is the minus of the input sinusoid. Correct? So this will be exactly equal to same amplitude, 180 degree out of phase. Stop, right? So if I sketch it on top of the original input, so this will become something like this. Yeah. So now note that here you have there was a sign inversion that was happening when it was going to this summing block, right? Plus and minus. Again, what I'll do, I'll say that the sign inversion is difficult to understand. I will do the inversion here. And then I will take the output with the assumption that now if I connect these two nodes, this will be the original network. Correct? So now what will this output be? It will not be 0. Why should it be 0? It will be the same as the input. Correct? It will be exactly the same as the input. Right? So it will be okay. So now let's do a thought experiment. The thought experiment is the following. Let's assume that I have a switch here, which was open. Till now it was open, and I was observing this output node, and it was giving me sinusoid of exactly the same frequency, same phase as the input. And let's also assume that I have a switch at the input side. And the switch was closed. Switch was closed, that's why the input was flowing in. So at any arbitrary time instant, I open this switch and close this switch. Right? Do you think anything will change in the loop? No, right? Because ultimately, so what is this G block seeing? This G block is seeing a sinusoid. It doesn't know from where it is coming. It need not know. It was originally it was seeing the input sinusoid. Now it is also seeing the same sinusoid, but this sinusoid is now coming from the feedback network. Right? So similarly, if the input to the G hasn't changed, the output to the G will not change. So the input to the H block will not change. So essentially nothing will change in the loop. So now your loop becomes self-sustaining. Right? Your loop becomes self-sustaining. You need not have the input at all. So this is a classic case of oscillator. Right? In an oscillator, you don't have an input. You don't have an explicit input. It gives you some output continuously. Right? So this is regardless of this is the scenario because you have hit this condition of 1 plus GH is equal to 0. No, why? I have opened the output. I have opened the input. Amplitude won't be doubled. Right? So there is still one source essentially. Looks like there is one source. Right? So this criteria is often also called Barth-Hussein's criteria. Folks who have taken control systems classes will know, right? So, but regardless of the name of it, this is the intuition behind why if you hit that point of GH equal to -1, your system will start oscillating. Now you might say that maybe this is happening at some frequency omega naught. If I change the frequency omega naught, maybe GH will be equal to not be equal to -1, then why should I care? The reason you should care is there will always be some noise in the system, and the noise can be of any frequency, not in your control. So the system can pick up a noise and it can start oscillating, right? So regardless of whether you are operating at any frequency for which you are satisfying this criteria of GH equal to -1, even if you are not operating at that frequency, you have to ensure that the system is set up in such a way that GH is never equal to -1. Okay. So if we have to ensure that, now let's go back to our two-port network model. If GH, we need to ensure that this GH is never is equal to -1. I think I made a mistake in this case, right? Okay. So if I have to ensure that this denominator never goes to 0, or what do I need to ensure? I need to ensure that this stuff never goes to 0. Correct? So in other words, I'll have to ensure that for stability purposes, one minus whatever this was, y12, y21 by here is never equal to 0. Or in this case, since we have assumed that all of them are real numbers and all, we need to ensure that this is okay. Let's keep it at never equal to 0. And if I write out V0 over Vi again, what do I get? Y21 GS. So now we assumed all these are positive values. You need not assume that all the time, but let's keep things simple and let's assume all this to be incrementally positive values. And if we have to ensure that this is never equal to 0, which means that I have to ensure that y11 plus GS times y22 plus GL minus y12, y21 is never equal to 0, right? So you cannot set this to 0, right? So one might then say, I'll not set it to 0, I'll set it very close to 0. I'll just cancel optimally, right? Maybe have a residue after subtraction to be 0.001, something like that. But that is a dangerous game to play because all these are functions of the IV characteristics of the device, right? They are incremental parameters, y11, y22, y21. These are derivatives of the IV characteristics of the device. Since the IV characteristics of the device can change with changes in temperature, changes in humidity, changes in pressure, and changes in voltage, so you cannot guarantee that it will be precisely set, given that you are essentially playing with fire, right? You are just at the edge of instability. So it's better to stay away from instability as far as you can. So what is the best way to ensure that your system is always stable in this particular case? You don't do the subtraction at all. you have to find out a network, or you have to construct a network in which this negative term goes to 0. Right? Does that make sense? Am I speaking too fast? Okay, so if you think that I am speaking too fast, stop me, ask me questions, right? Otherwise, I don't get feedback from you, I can run away. So this term has to be set to 0, right? So now I can be set to 0 in one of 3 ways. You either set y1 to 0, y21 to 0, or set both to 0. So which one do you think is the, given that we want an amplifier, which one do you think is the, yeah. So why not y21? Right. So y21 essentially is my forward gain, right? So y21 is that one that is responsible for taking the signal from the input port to the output port. And I also saw here somewhere, right? Where was G? So G was proportional to y21. So if we want large gain, we'd want large y21. So we don't want to set y21 to 0, which means that only one option remains, which means set y12 to 0. Right. So this is to ensure stability. And naturally, the other outcome that came out was we need to set y21 to as high as possible, right? Tending to infinity. I mean, nothing is infinity, we know, but I mean, we are making a wish list, then why not put infinity in our wish list? So this is to get high forward gain. Okay. So now, what remains? I have this y11 and y22 to deal with. So what do you want now? Let's say y11. Ideally, now the denominator is entirely positive, right? So your if I do this, if I keep y21 as is, then your v0 over v1 is minus y21 gs by if I want to maximize v0 over vi, then clearly I need to now minimize, given that I know the denominator will never go to 0, I have to minimize the denominator. And the easiest way to do that is to see if we can make both y1 and y22 to be 0, right? So we can make y11 0 and y22 to be 0, right? So essentially the wish list matrix for my y parameters is 0, 0, infinity, 0. Right, so this is the wish list. Now, obviously, this is not possible. You cannot either make anything, I mean, go to infinity, or one might argue that one cannot make anything go to 0 also. But this is, since we are making a wish list, this is something we should target to achieve with as high degree of precision as we can. Right? So now, yes. Pardon? No, this is a wish list. We don't know how to do that till now, right? This is what we want. So ultimately, if you are targeting something, you have to figure out what you are targeting. Infinity, we know we'll never be able to achieve. But essentially, what I mean is as high as possible. Correct? Okay, if you are not comfortable with this, let me just keep it as y21 and say y21 should be as high as possible. Okay. Okay, so now this is again all algebra. I would like to see the implications of this as to why this makes sense. By the way, I mean, an example that I normally give while talking about these feedback and oscillation is a classic example that can be classroom demonstrated, is that of a microphone and a speaker. So if you have a, let's say, microphone and you have this speaker, and in between you have an amplifier, right? So this we established earlier. So if this stuff this network is supposed to be unilateral, then I'm speaking into the microphone. Signal is flowing, getting amplified. This A now has a battery extracting power from the battery and blasting the signal out here, right? This is unilateral. You can say 2-port, right? You have 1-port signal going in, another port signal coming out. But as it turns out, if microphone and speakers are nearby, then this is not particularly unilateral because some part of the signal is flowing back into the microphone. Right? So that's what it keeps on happening. If I go close to this guy, right? Right. So this keeps on happening. So why does it happen? This is equivalent to saying that I am increasing this feedback factor, right? So you can assume that there is some sort of transfer function H kind of thing here. If the part of the larger part of the signal is getting intercepted and going to the output, then it's possible that you hit that spot of GH is equal to -1 and things can start oscillating. Okay. Other way to see is that other very common thing you must have seen if you attend any function or somewhere, whenever there is a this type of scenario, somebody points to the person who is controlling the amplifier and says, do this, right? So it's basically decrease the gain, right? So you decrease the gain. So if you decrease the gain, then naturally, I mean, your GH is a function of both the forward path gain and the feedback factor. And normally this feedback factor is not changeable dynamically. I mean, here I was able to go close. I can as well go far, but normally you will see these theaters and places where these functions take place. They are very well acoustically shielded in the sense that they have good absorbers, right? So the reason you have good absorbers is because you are setting H to 0. You don't want Y12, in other words, right? So you don't want any reflection to come back into the microphone. So again, and these are examples of various feedback systems, not only electrical, in multiple other domains. I mean, all I'm saying is that you should keep your eyes and ears open to see the operation of feedback in daily life. And you will see that in this course also, feedback will come back in multiple ways in few classes from now. Okay. So that is a piece of trivia anyways. So let's go back to our circuit design. So when we are essentially saying that we want Y11 to be 0, Y22 to be 0, and so on and so forth, what are we essentially saying? We are saying that so this was Y11, this was Y12. So Y12, V2 going to 0, we discussed in fair amount of detail. So now, what is the implication of why? So from the circuit perspective, why do we think, if I see on the on this part of the network, what purpose is Y22 going to 0 serving? Right? I mean, in terms of currents and voltages, having a Y22 and not having a Y22. So it looks like not having an Y22 is a better thing to do from the algebra that we just did, right? Setting Y22 to 0 was good because the denominator was going down. But now if I switch to the completely circuit domain of understanding, or I want to explain why Y22 should be 0, looking at a circuit, then what explanation can you think of? No, I'm only talking about this part of it, right? So forget about input part, output part of the network. Right. So more transfer to RL in the sense that this current Y21 V1. Firstly, this current Y21 V1 is not getting affected whatever I do to Y22 RL, right? That is independent of whatever is getting affected, whatever I do to Y22 and RL. right? So that's why it's a current source. It's not depending on whatever is loading it. So now, if I have to maximize V naught, right, I have to ensure that entire of this current flows into or flows out of RL. Right? Nothing should go anywhere else. If something goes somewhere else, I have current division, I'll get less voltage. Right? Other way of thinking of this is that you have parallel combination of RL and Y22. So lower resistance, current flowing into a lower resistance, you are getting a lower voltage, right? So in order to maximize V naught, only by looking at the output side, it's beneficial to set Y22 to be equal to 0. Or if you think in terms of resistance, if this is R22 or R naught, the R naught should be infinity, right? Which means it should be an open circuit. If I exclude RL and look from this side, it should be an open circuit, right? So this should go to 0. This should go to 0, right? Y22 should go to 0, but your R naught should go to infinity. Make sense? Similarly, if I try to understand why should Y21 be very high, this is quite self-evident in this case. Y21 is responsible for taking the signal from the input port to the output port. We would want that to be as high as possible. Now let's turn our attention to the input side of the network, right? So why should Y1, what purpose is Y11 serving? Why should Y11 go to 0? This is some resistance, right? I mean, think in terms of resistance. Now, it might be helpful. Let's say I say this R11. Correct. So there, yeah, exactly. Drop, right? So that's the issue. So this is your V1, and the current that you are taking at the output port is proportional to V1. So if V1 is lower than what it can be, then the current that you are instigating or that you are driving at the output port is potentially lower. So ideally, you would want maximum signal transfer or maximum current into the final load RL. But if V1, since the current is proportional to V1, you would want V1 to be as high as possible. What is the maximum that you can get? In principle, you can get V1 equal to Vi if R11 is infinity. Correct. So in other words, what I'm saying is your input port, the input side is like this. This is V1. I want V1 to be is equal to V1 to be as high as possible. In this case, V1 can be at max Vi when R11 tends to infinity. Right. This is the wish list. Right. So R11 tending to infinity is equivalent to saying Y11 tending to 0. So we want Y11 also to tend to 0. Okay, so the problem is ideally, yes, you can make RS equal to 0 in this diagram, but the issue is this stuff is not in your control. Right? The source has its own impedance, and source will probably come from something, a previous stage. Maybe you are making an amplifier where you have one amplifier is driving another, one block is driving another. That will have its own internal impedance. So you cannot change that. Just like you cannot change RL typically, right? Your load specification will be given to you. So RL you cannot change. Typically, RS you cannot change. You have everything between that in your control, right? So then you have the part of the motivation of the course is essentially to design this. Now you are still in this Y12, Y11 parameter in this regime. Later on, you will see that we'll replace them with actual devices, and then we'll see what are the constraints that further emerge. So to cut a long story short, Vi and RS is not in your control. It's a user specification given. So somebody has asked you to design an amplifier. Whoever has asked you will also give you the specifications of this is the input resistance, this is the output resistance, and then design me something in between. Okay. Okay. So if this is the scenario, then what is the effective cut down model of our amplifier? So if this is the input, and this is your RL. So from the input side, essentially everything goes to 0. Y1 to V2 goes to 0. Y11 goes to 0. So input side becomes open circuit. So the stuff you have this box, right? The incremental two-port network box. So this input side is open circuited, and the output side you have Y21 V1, V1 V2, and that's it. Okay, so this is my block diagram of an ideal incremental block diagram of an ideal amplifier. Okay, does it make sense? Okay, so if this is the block diagram of an ideal amplifier, what will ultimately my V0 over Vi be? Now this is pretty straightforward. Tell me quickly. Now look at the network and tell me. Like, you don't have to put everything in that equation. Input is V1 is equal to Vi. So V1 is equal to Vi. This current then becomes Y21 Vi. This entire Y21 Vi flows out of RL. So the voltage that accrues across RL is minus Y21 times RL times Vi. So the gain is, the voltage gain is minus Y21 RL, right? Okay. So now this is as far as the voltage gain is concerned. What about the power gain, right? We have been discussing from the beginning of this course, we have been harping on power gain. Do you think we have power gain? When I say power gain, I'll have to then characterize it by saying that there is some input power, there is some output power. So the ratio of that, the power gain. Okay. So what is the input power? Why V squared by which R? Which V? Which R? I can't hear. Can you speak aloud? What is the power that is getting delivered to the network? What is P? V1 I1. What is I1? 0, which means power delivered is 0, right? Power getting into the network is 0. P in is 0. What is P out? Right? P out is now V0 squared over RL average, which is essentially Y21 squared Vi squared average by RL, right? So is this 0 or non-zero? And quite high, because ultimately, if I am able to make this amplified, this should be quite high. So what is the power gain? Infinite, right? So your power gain looks to be infinite in this case. So AP is equal to infinite. So does that make sense? Or am I playing tricks? Yeah, ideal case, fine. So what type of non-ideality do you plan to use? Maybe I'll have some input resistance. Instead of Vi, you will probably have alpha times Vi at the input, right? Okay. So essentially, you are saying that we are not taking into account the quiescent picture, right? So where from is the extra power coming? It is coming from some DC source, right? Ultimately, power conservation holds. So I have stripped away the DC sources and all, but where from are these control sources arising? These control sources are not not RLC circuits, right? They are something else, right? So they derive power from somewhere else, from some supply, right? They are derivatives of IV characteristics. So essentially, an IV characteristics of a device has to exist in order to get Y21, right? So, and you cannot say that I'll buy the device as 0, 0, right? No V, no I, and get Y21. You'll get 0 Y21 also. So it essentially means that in order to get some decent Y21, you have to burn some power in the device. right? So if you take the total power, right, the quiescent power plus input power, that will always be less than the total output power. But in this picture, we are not showing the quiescent power. Okay. Does that make sense? So in truest sense, power conservation still holds. You are not as if you are getting more output power than input power, but what you are getting is you are getting more, you can get more power at a certain frequency than the power you are extracting from the source at that frequency. That you can get. Power conservation doesn't really tell you that the power conservation has to hold only at a certain frequency. It only tells you that the total power at the output will be less than or equal to the total power that is going into the system. Okay. Okay, fine. So this is something that you should also keep in mind. I mean, suddenly you see gain, you get power amplifiers, and then you start thinking fire from, I mean, something is wrong, right? Okay. Fine. Any questions? Yes. Yes.
And what's the other power that you
So in this case, I mean, in this picture, you don't have a battery, but you have a source, right? You have VI as the input source. So it's potentially you can draw power from the input source. In this case, you are not, but in a general case, you can. I mean, if this input was not infinitely large, right? If Y11 is not equal to 0, you would have gotten some I1. Correct? So because you would have gotten some I1, you would have extracted some power from the input source also, right? So there are essentially two sources. One is a battery, which is invisible in the incremental picture. One is a incremental source, which is visible. So when I say P in equal to 0, what I mean is that the power drawn from the P in, or from the visible input source is 0, but there is a battery which is invisible, right? You are drawing power from there, and that is from there only you are getting these Y21 terms, right? So the genesis of Y21 is because you have a finite non-zero IV characteristics with certain slopes. Okay. In order to generate those IV characteristics, you have to naturally give some I and some V, right? Give some V and Y, which means you are burning power. And the power that you are burning will be evident from the IV characteristics that at which you have biased your network. That's all. Okay. Okay. Okay, so now since we have this, now we are still in this incremental domain, but ultimately we need to figure out what is the desired IV characteristics of a network for which we will get these incremental parameters, right? Because ultimately we are looking for not only the incremental parameter, we are looking for a full network. You cannot really tell your customer that this is the incremental parameter, you get me a device like this, I'll make. So getting the device is also your job, right? Making the network is also your job. So so now let's try to reconstruct what will be the desired IV characteristics under the condition that we want these type of incremental parameters, right? So we want, let's start with the Y11 parameter. Y11 should be equal to 0. So when I am saying I want Y11 to be equal to 0, what type of IV characteristics I am looking at? I mean, let me rephrase that question. So I know now I am going to the full-blown network, right? So this is F of V1, V2. F1, V1, V2, F2, V1, V2. These currents, these are basically currents, right? Again, there is a battery. Maybe the battery is sitting inside. So now you have essentially 4 variables, right? I1, I2, V1, V2. 2 of them are dependent, 2 of them are independent. In this case, the way we have been dealing, voltage, input voltages are independent and currents are dependent. So essentially, you can have 4 plots. One with respect to V1, while you are varying V1, plotting I1, while keeping V2 same. And then you vary V2, plot I1 while keeping V1 same, and so on, right? So you have 4 different plots, and that's from where you get the 4 different Y parameters. So in order to find out y11, which plot should I be focusing on? What I'm essentially saying is you have these 4 plots. So I1, B1, you have I1, B2. You have I2, B1. You have I2, B2. So yeah, so clearly y11 is by definition dou I1, dou B1, right? Under a quiescent condition of some B1Q, B2Q. Correct. So y11 equal to 0 under some quiescent condition of V1 to V2Q means that, I mean, let's mark off a quiescent voltage V1Q. And when I say y11 is equal to 0, what do I essentially mean in terms of the absolute IV, total IV characteristics? y11 is the slope, right? y1 is the slope of I and V. So if slope is 0, what does it mean? It should be a straight line parallel to the voltage axis, right? So it should be a straight line. It should be a straight line around the quiescent point. It doesn't really say what is going to happen as you deviate from the quiescent point. We are taking the slope at the quiescent point, and the slope at the quiescent point is expected to be 0, which means it has to be flat. IV characteristics have to be flat. It doesn't also say that whether it's like if I1 is 0 or 1 milliamp or 2 milliamp, doesn't really matter. It has to be flat. That's all it says. Similarly, in case of when you say y12 equal to 0, again, y12, to extract y12, I have to look into the plot of I1 versus V2, right? And again, okay, so let me take a step back and let's come to this first plot again. This plot, in the first plot, this is under the condition that V2Q is fixed. Correct? So when I am taking a partial derivative of del I1 del V1, I'm assuming that V2Q is fixed, right? So if V2Q changes for the same V1Q, I can have a different set of curves, right? Well, let's concentrate on only one curve for the time being. Similarly, for y12, I probably have, again, if I have, let's say I have biased it at some V2Q, this will again be 0, which means that my again, so this will be some constant, right? So let me extend it a bit, otherwise it doesn't, looks like a point. Similarly, in case of y21, question? So in case of y21 is what? Dou I2, V2, dou V1, right? Under again a quiescent condition of V1Q, V2Q. And I want y21 to be what? High or low or 0 or what?
High.
As high as possible, which means I want what should the expected IV characteristics be around V1Q? Parallel to the y-axis, right? It should be, if it's parallel to the y-axis, it's infinity, right? The slope is infinity, or in other words, I can say it has to be very high, right? So don't go to infinity, maybe I make a steep slope. So similarly, y22 equal to 0 means again you'll have V2Q, and this will again be flat. Okay, fine. So again, you should note that all these plots are valid. The only inference that we can make from the incremental y parameters while we are trying to recreate the full IV characteristics is the fact that we can only make a judgment on the slope of the plot around the quiescent point, right? That is number one. However, your signal right? Your signal is not necessarily of zero amplitude, right? Your signal will have some finite amplitude, which means that signal will swing. When the signal swings, right? When the signal swings, what can you call? Let's say you're in this case, if VI swings, if VI is, let's say, VP sine omega naught t, and this goes up by VP and down by VP, what can you comment on? Which plot should I concentrate on in order to figure out which side, how the quiescent point can get affected at the input side? Okay, the question might be confusing. So what I'm essentially saying is your VI is, let's say, VP sine omega naught t, and VP is not like a very small incremental input. VP, let's say, is 100 millivolt, right? So one of you pointed out a few minutes back is that I have not shown the bias at the input side, right? The reason we didn't show the bias at the input side was because we were concentrating on the incremental picture. Now, it's quite evident, it should be quite evident from our discussions till now, we cannot simply add an input and hope to get an output. There has to be some bias. When I say there has to be some quiescent voltage or some bias, in this plot, what am I referring to? I'm essentially referring to if I null the input and look at the input port, what should I see? I should see a voltage of V1Q, right? That's what quiescent point means, right? We don't have any incremental input, and I'm observing the voltages across the ports and the currents to the ports. If at the input terminal, at the input port, I should be seeing a voltage of V1Q and the current of I1Q. And the slope of the IV characteristics around V1Q, I1Q should be equal to 0. That's all we know till now. Agreed? Do you want me to repeat? Well, let me repeat anyhow. So when we are saying, where was that thing? Okay. So ultimately, we have some battery inside or somewhere, and I'm applying this, correct? When I'm trying to find out the quiescent point, what am I saying? I'm saying that even in the absence of VI, I will get a finite V1. And then V1 will be equal to V1Q. Correct? Similarly, this I1 will be equal to I1Q, whatever that might be. So in the IV characteristics, where will I find that V1Q, I1Q? I will find that in the first plot. And all I know is that the slope of I1 versus V1 is 0 in order to get my desired incremental parameter, right? It's the interplay between the total IV characteristics and the incremental parameter. Okay. So now, if this is what it is supposed to be, and I now say that I put the incremental input back, then can you comment on when the input is swinging? When the input is swinging, can you comment whether V1 is held constant or V1 is also swinging? Is it? I mean, when in the presence of input VI, is V1 held constant or is it changing? It's changing. If it is constant, then you will not see any change in I1 or V1, right? Which means you will not see any change at the output also. It's equivalent to saying I have a fixed battery, I have connected it there. Whatever happens rest of the universe, the voltage will not change, right? So naturally, we are expecting from the incremental model of the transistor also, what we are expecting, the input VI should arrive completely at the input port. In the total picture, in the total picture where I'm trying to find out, where I'm trying to draw a conclusion of what is happening to the total voltage, this essentially means that that incremental VI is riding on top of some quiescent voltage, right? It's riding on top of some bias voltage, which means that we should expect the input voltage to also, at the input, by input means in this case I'm referring to the voltage at the input port to also change. So why am I harping on this? The reason I'm harping on this is, when in the presence of the signal, you would expect this region of operation in the IV characteristics to not be located at only one single point. It can go this side, it can go that side from the quiescent point. Does that make sense? Right? So again, I mean, when you are trying to make an amplifier or make any circuit, you have to ensure that the region of operation is, the switch region of operation is not limited to only one point. Then you are not allowing for any signal swing. Okay. So if you have to allow for a signal swing, which means that you have to ensure that this Y11 is not zero only at one point. It has to be zero at over a range of points, right? Which essentially means that this slope has to be flat over a range of points, right? So essentially this has to go over a range of points. So this is in order to accommodate the signal swing. Okay. So this holds true for naturally all four plots, right? So this also will go over a range of points. This is also over a range of points, also over a range of points. Now, what is the range is a matter of specification, matter of the network that you're using or the device you're using, but nonetheless, this is an wish list till now. Okay. Any questions till now? Okay. So, as it turns out, I'm sure you have done this in your UG curriculum also. One of the most popular devices which give us something similar is a transistor. Now, there are various flavors of transistors. The one that we will be sticking to in this course is a MOSFET. And a MOSFET essentially is a device whose in terms of IV characteristics or in terms of the two-port network, let me sketch the device first, then we'll discuss the IV characteristics later. It's a 3-terminal device, right? It's a 3-terminal device where one of the terminals is shared between the input port and the output port. And the nomenclature is, this terminal is called the gate. One of the other terminals is called the drain. We'll get to which is called drain, which is called source later. And this common terminal is called the source, right? Popularly abbreviated as G, D, and S. Okay. Also, as it turns out, in a MOSFET, the input bias current I1 is actually 0 at DC. We'll expand on that why at DC later on, but your input bias current is absolute 0, right? So if the input bias current is absolute 0, then naturally that's the best case solution for us, right? So if the input bias current is absolute 0, regardless of what happens, then both your Y11 and Y12 will go to 0, right? So no worries about that. So that's great. So since so this is I1, this is I2. So So now let's say, I mean, obviously now I am the full-blown picture, not the incremental picture anymore, right? If I am given the full-blown picture, and let's say that there is no battery inside, or the batteries are somewhere sitting outside, right? So what I mean is that only there are 2 ports available. Let's say I have battery here and I have a battery here. There are no battery inside. Okay. So this is V1, this is V2. What is the power consumed by the box? Correct. This is V1 I1 plus V2 I2. V1 I1 is 0 because I1 is 0. So power consumed is V2 I2. And can you comment on V2 I2 will be positive or negative? Negative means it's generating power. Positive means it's dissipating power, right? So is drawing power or can it generate power? Can it generate power? A MOSFET without any voltage source inside? Nothing can, right? You need a power, you need a voltage source, or can somebody turn off that beep? Okay, let it be, maybe 1 minute. So it doesn't have any battery. Let it be. It doesn't have a battery or a current source inside, so it cannot generate power on its own, right? So this guy has to be greater than 0, greater than equal to 0 at least. This is simply by law of power conservation. So if that is the case, and I turn our attention to this plot, I2 V2 plot, right? So if I turn our attention to this plot, what is it telling you? It's saying that if I2 times V2 has to be greater than 0, which quadrants can I2 V2 reside? Which quadrants will the plot reside? First and third. It cannot go to second and fourth, right? So all I know is that this guy is here, and it can possibly be here, but it definitely has to come through 0. Right? It cannot go to anywhere else, otherwise I am violating law of power conservation. So somehow it has to drop, somehow it has to go this, it can go like this, it can go like this, I don't know, but I mean, that's all it's saying, right? It is some non-zero value, then it has to go to 0, and maybe it can go to the third quadrant, right? Okay, fine, we'll stop here. We'll meet on Saturday.